Welcome to lecture 12 of the course. We had spent most of the previous lecture discussing what are the desirable properties of this duality transform, right. Just to recap, so we are trying to solve this problem of intersection of half planes, okay. And somehow we wanted to use our prior knowledge of constructing convex hulls in 2 dimensions. So, we just hypothesized that there is this duality mapping D, which maps points to lines and maps lines to points, such that these properties are satisfied. That's it's self inverse, it's 1:1, and there is this thing called incidence property, that if a point P is incident on line L, then the dual of line L, which is a point, is incident on the dual of the point P, which is a line. And then from that, one of the consequences is that if L1 and L2 pass through a point P in the primal space, then the dual of these lines, which are points, okay, will lie on the line that is the dual of that intersection point. Okay. That follows from the previous property. And then there is another important this orientation property, which is calling the above below property, that if a point P is above L, then the dual of the line will be below the dual of the point. Right. So, and using these properties, so I could show you that there is a close and intimate connection between the problem of computing the intersection of this downward half planes. Okay, not the entire set. We partitioned the set of half planes into downward and upward. So, the downward intersection of downward half planes has a 1-to-1 correspondence with the lower hull of the dual of those lines describing the half planes. Okay. So, this is where we stopped last time. So, everything was fine except that I did not give you any concrete examples of such a duality function. Okay. So, let me do that today. The kind of duality function that there are a number of such duality functions that satisfies the properties that we mentioned. The one that I will be picking up has some special significance, which we will see again in the course of this lecture. So, what we will do is the following. So, the point again is a pair of coordinates, right. So, a point P is some kind of coordinates, let us say x prime, y prime. Okay. And the line is specified in the slope intercept form. So, it is the slope and the y intercept, right. Now, d's of P I am defining as x prime y prime is mapped to okay, actually let me change the notation so that there is no confusion later on. Let me use a b instead of x prime y prime, because normally use the parametric equations in x and y, right. So, let me change that to a and b. So, a b will be mapped to this line L given by y equal to 2 a x minus b. In other words, this is my m, okay, and minus b is equal to c. C equal to and vice versa, that y d's of L given by y equal to 2ax minus b, okay, will be mapped to the point AB. So, this by definition becomes a self inverse. Let us try to verify at least. So, self inverse property is verified by the way I have defined it. So, let us try to verify the incidence property. So, incidence property. Suppose P lies on L. Okay. So, L is my parametric equation mx plus c. Okay. And this is given by AB. So, it satisfies that, which means that this AB must satisfy this equation, right. So, implies AX. So, just a moment, what am I saying? Just a moment. What am I saying? Right. So, that was the confusion, right? I missed that y. So, which means that implies P is equal to AX. Oh, sorry. What am I saying? AM plus C, right? Okay. Now, what is the dual of the point? That is the line given by y equal to 2 ax minus c, sorry, minus b, right, and d of L is given by m by 2 comma minus c. Is that right? So, this is now a point and this is now a line. So, let us again substitute. So, does it satisfy? So, question is y, sorry, y is minus c, right? Is minus c equal to 2. So, this is my equation 1, maybe I should write it as 1. So, 2 a x is m over 2, right. That is all right. I mean m x, the line is minus b, right. So, is it equal to this? So, or is minus c equal to, well, I will just transfer anyway. So, let us a m minus b, or is b equal to a m plus c, which is exactly the same thing as equation 1, right. So, this is certainly true. right. So, the incidence property is satisfied by this mapping. Right. I will leave it as an exercise for you to verify the other properties, the above below condition. Okay. Other properties basically means the above below. The property 3, which is the point, sorry, 2 lines meeting at a point, will become 2 points lying on the line. So, that follows from this property anyway. So, that need not be proved separately. So, prove the above below property strictly. Okay. So, just from this mapping. So, what at this point it just looks like some symbols, some symbol pushing, and somehow magically this seems to work out, and assuming that even the above below property holds. But what is a more intuitive thing? So, for the more intuitive thing, let me draw your attention where this transform is coming from. Okay. So, consider okay, let me go to a fresh page. Okay. So, consider this parabola y equal to x square. So, consider some point A on the x axis, this is x and this is y. So, A of course, so this point corresponds to A square. Okay. Now, this particular parabola, okay. So, what is the equation of the tangent at A square? Can you work on it quickly? Do you remember enough of your analytical geometry? No, just tell me the answer. I don't want to know how you calculate. So, what you are saying, y equal to 2ax minus a square. Great. So, you remember it pretty well. So, does it now ring any bell? So, this transformation, that the duality transform that I defined has this, this point A B, okay, is mapped to 2ax minus b. Okay. So, at least why are we using this constant 2 here? I mean, I could have simply written something else. Why this 2 is kind of explained by this 2. Okay. So, what are we saying? So, what we are saying is that if the point is on the parabola, okay, if the point is on the parabola, so the dual transform of that is what? The tangent itself, right? So, what is the dual of a square? D of a square. By your definition, it is y equal to 2ax minus a square, right. So, it is not a coincidence. So, the tangent at a square is the dual transform of the point, if the point is on the parabola. How about points not on the parabola? So, point not on the parabola, so the point could be either above or below, right. I could take A, I mean with the same x coordinate. Okay. So, one possibility is the point is above, okay. The other possibility is the point is below, may not be on the parabola, right. So, it is the same slope, that is the way we have defined the dual transform, right. The slope remains same, the y intercept changes, and if you calculate, we will find that if the point is above the parabola, the point is above the parabola, the dual transform is going to be parallel to this So, first of all let me draw this tangent. This is the tangent if the point was on the parabola. So, for a point above the parabola, you can show that the dual transform will be below the parabola, and not only that, it will be shifted by something like. So, this is a comma b. See, it is not b minus a square. Okay. So, this point will map to something that is b minus a square. Likewise, the point below the parabola will be mapped to a line above the parabola, again with this kind of the intercept will be. So, you just take the signed difference and that will be what it is. Okay. So, this is the geometric interpretation of this dual transform. So, when you go to higher dimensions, what happens? Can you guess what should be the dual transform if we use the same kind of idea for the dual transform? So, then you are talking about a. So, in higher dimensions, okay, you then talk about a paraboloid. Okay. So, let me not use y and x, but let me use, let us say x 1, x 2 all the way up to x d. These are my in d dimensions, I have these as the coordinates. So, then my paraboloid is defined as again some constant. Okay. Oh, sorry, whatever. I am not. Let me not the shifted parabola, just the parabola y equal to x square. So, then if you again look at the slopes, you take the partial derivatives with respect to all the coordinates, right. So, the del x d by del x I is 2 x I, right. So, then can you guess what should be the dual transform in the higher dimensions? So, d of the point, now point in so it is a d dimension point. So, we are talking about a 1, a 2, a 3 up to a d. So, can you guess what this should be, the dual transform of this point? Right, 2 a 1 x 1 plus 2 a 2 x 2, same thing, plus oh sorry, what am I saying? Just a moment. Yeah, I have to write that. Ooh. Sorry. Right. So, this is what it will work out. So, again the geometric interpretation remains the same even in the high dimensions. Why use this? Well, the same thing if you want to compute the. So, we have not studied about, let us say, constructing convex hulls in 3 dimensions or higher dimensions, but what this says is that if you know how to construct the convex hull in 3 dimensions, you can use the same algorithm to compute the intersection of half spaces in 3 dimensions and in higher dimensions. Why use the paraboloid? So, this is a specific transform that satisfies the the properties that we mentioned. So, this is one kind of transformation that satisfies all those properties that we desire from the duality transform. There are also other kinds of transformations that work. Okay. There are at least I know of about 3 or 4 other kinds of transformations, okay, that satisfies those properties, and you could use any of those transformations, okay, such that you could go from this convex hull to intersections, okay, because all those transformations satisfy the basic properties that we discussed. Okay. This is this paraboloid transform. I'll just give you another nice property of this paraboloid transform, not just for this thing, but we will be able to make use of it in some even more non-intuitive applications. Okay. But just note one thing, that here the transformation is not defined with respect to in 2 dimensions with respect to vertical lines, because the above below does not hold there. So, there is some singularity, or let us say that one in the dual space of lines, one line, the vertical lines basically have no counterparts. Okay. Similarly, for any of the other transformation, I am not getting into the details of those, there will be one singularity point, and there is a basic fundamental geometric limitation why these transformation will have one point of singularity. Okay. So, especially if you are familiar with projective spaces, this is also one kind of projective space actually. Okay. So, let me talk about another nice property of this paraboloid transform. Okay. Okay. So, okay. So, here is my parabola. Okay. Here is okay. So, I am drawing the tangent at a comma a square. This is my tangent at a comma a square. Let us call this distance, which is getting a little cluttered. Okay, this distance I am calling d. What is distance d? So, I am looking at the tangent at a comma a square, and I have a point, I have a point b. So, this is b comma b square, and I am looking at the distance of the parabola at b comma b square, the vertical distance, okay, to this tangent, which I am calling d. Right. Now, d is equal to how much? Well, yeah, right, whatever, b minus a whole square or b minus a whole square. Okay. So, this is just follows from this formula. So, this thing can be interpreted as the following. So, if this point, so I am talking about 2 points now, one is this a square and another is b square. So, if you look at the projection of the points on the x axis, okay, namely this a and b, okay, the distance between this, okay, is b minus a, right. Okay. So, this is distance in the projected, or let us say the projected distance on x axis, or whatever distance. Okay, sorry. So, as if I have just projected those points from the parabola to the x axis. So, that is the distance. So, that distance square is equal to d. Right. So, what it says is that further the point, if I take another point C, okay. So, another point C basically, and I look at, well, I mean, so again the vertical distance of C comma C square to this line, okay. So, it is sort of directly proportional to the projected distance on the x axis, right. So, we will just remember it as the following, if the distance on the x axis between 2 points is more, the vertical distance that you obtain from the parabola to this point is also grows. It grows as some square, but essentially it is proportional. The larger this b is, the larger is the distance. Okay. So, in future, when we talk about things like finding closest neighbors and discuss about Voronoi diagrams, okay, we will see that there is a very close link using this transformation between what is called the three dimension convex hulls, okay, and Voronoi diagrams. So, like we could get these for free, that this 2 for 1 deal, right, convex hulls and intersection of half planes. It turns out that there is a very similar relation between a 2D Voronoi diagram and a 3D convex hull. Okay. Right now, I will just leave it at that, and I am only drawing your attention to this property. Only this property will be used to, and this works for any kind of. So, I have moved from x, the projection is along x, right, and the parabola is a 2-dimensional curve. So, if I take the set of points from x and lift it to this parabola, which is 1 dimension higher. Okay. So, essentially what I am saying that in general, if I take these points on d minus 1 dimension and project it to a parabola which is a d dimensional paraboloid, okay, then I have some kind of relation between the distance in the d minus 1, okay, and the vertical distance from this parabola to the tangent at this point. So, if you are looking for, so I am given this point A, this point, and I am trying to find the closest point. So, that has clearly some relation between this relation in terms of the vertical distance of this point. So, whatever is the distance, distance between A and B or distance between A and C can be captured, at least the relative distances can be captured by this vertical distance from a paraboloid. Okay. So, that leads to, so we'll do it more formally later on, there is exact one-to-one correspondence between Voronoi diagrams and convex hulls, but with one dimension gap. So, 3D hulls and 2D Voronoi diagrams, that kind of thing. And therefore, even when you study what is called the structural properties of Voronoi diagrams, that follows from the convex hull in one higher dimension. So, this really sort of simplifies a lot of things that people study about Voronoi diagrams. Right. In general, what we will study will go beyond this, and we will talk about what are called arrangements of lines and arrangements of hyperplanes. So, that has basically, so we will all pull it together later and show you how they all correspond. Right. So, for now this is all I will talk about duality. Any questions at this point?
So, in the higher dimensions, you have these points transforming to lines and vice versa. But what about faces? There is no transformation for faces. I mean,
No. So, the transformation is defined for all dimensions, right?
no, but it's only points going to lines.
Points going to lines and lines going to points.
Like if you have a face, there is no transformation of that, or you just apply individual.
No. So, essentially this is a point hyperplane transformation, right. So, if you are talking about a d-dimensional space,
Okay.
you are mapping it to another d-dimensional space. One is I am calling the primal space, and it is called the dual space. And so, this particular duality mapping is a point hyperplane transformation. There are other kinds of transformations people talk about, but for the kind of problems we are looking into, this point hyperplane transformation is the one that is most important to us, or very useful to us. So, this preserves the dimension in some sense, although they are two different spaces. Okay. Always remember the points, the space of points and space of lines, they are not the same space. Okay. It is the dimension of the space is the same, but we are not talking about the same space. It's one is the space of points, another is the space of lines, or space of points and space of hyperplanes. Right? There are other kinds of transformations where this preservation of dimension is not necessary. Okay, the things like when you go from segments, which are actually, see, it's basically how many coordinates do you require, how many parameters do you require to capture an object. So if you think about a line segment, how many parameters do you require to capture a line segment? 2 points, right? Which basically means 2 coordinates each. So it's like it's actually a 4-dimensional object. Okay, so there is actually a transformation between lines and some kind of curves in the 5 dimensions called Plucker coordinates. So there are various such things people have studied in geometry, and some of them we are useful for doing computational geometry. So since I am talking about already 4 and 5 dimension, I will spend the rest of the lecture today and probably the next lecture also, which I have sort of been postponing for a while, is talk a little bit about how lower bounds are derived for geometric problems. So let's use one running example, and so okay. So right now let's worry about this problem. Let's call it problem So if I am given a point set like a set of elements which have the following values 0.3, 1.1, 1.56, 1.1, 2.8. Okay. So this set of elements clearly has a repetition because these two have the same values. So the answer, so it's a decision problem. Okay. So decision problem which has a yes no answer. So this if you consider this particular instance, then the answer is it's no, right? It's not unique. On the other hand, if I change it to 1.15, then the answer is yes, all elements are unique. Of course, these elements can be drawn from all kinds of universe. Okay, so if the element, suppose xi's are from this set, what would you do? What is the easiest way of? Right. So it's the easiest way to do it is basically hash, right? So I have an array of size n corresponding to the value of each element. I hash, and after I hash, I find out. So essentially, indirect addressing, right? So with indirect addressing, it takes order n time. Fine. What if I do this? Why?
I can still hash, but there will be some collisions in my potential.
In each edit it can be further and
Well, at least I made you think. You can hash, fine, but after hashing, first of all, when you hash, there is one problem about hashing that people always forget. How do you initialize? There is a space. Hashing is about using some space, right? And that space somehow needs to be initialized. So if you are hashing in n square space, that's a problem.
N locations.
Okay, you're going to use n locations. So when you use n locations, what are you going to do?
there would be collisions.
I mean, hopefully, I mean, the hash function has to be such that, I mean, if I go
So each of
I
these does
not
not
equal to
contain too
j,
many elements.
h I not equal to it will at least
Well, so you are getting into somewhat non-trivial things, right? There should or should not be collisions. How many collisions will be there? So, well, I mean, if you have done a course with me on algorithms, you may have someone would have blurted out, okay, use universal hashing, right? Does it ring a bell? Okay, I'm not even going to get into those kind of scenarios, but I claim that there is an even simpler way to think about it.
Parabola to the x-axis.
No. So, well, I mean, so that you can forget about parabolas, n to the power 5. Someone should blurt out the answer by now. Don't think always about linear time solutions. I'm not saying that you have to give me linear time solution, but what would be a natural way of solving this problem? Yeah, right. I wanted to hear that. So if you sort them, then of course any repetition will be in consecutive location. After sorting, it can be checked in linear time, right? So now if I want, can I sort these elements quickly? Huh? No, come on.
Oh, I know the range.
Right, you know the range, right? And it's a polynomial range. So what do? Yeah, well, I mean, you call it various things. I call it radix sort, right? So radix sort means for any range which is polynomial, you can do it in order n time. Are you familiar with this? You just run your buckets from 1 through n and you repeat c times, and it has to be a stable sort to be able to apply radix sort, right? I don't know, people always forget about radix sort. I don't know why. I mean, people remember merge sort, insertion sort, all those useless things, probably not merge sort, but insertion sort, but somehow people never think about radix sort. I mean, I emphasize so much of radix sort when I teach algorithms, and still people, well, anyway, people who have done the course. So you can't do radix sort unless the sorting is stable. We can take it offline in the class.
I thought you were saying that for this problem we need a stable sort.
No. So radix sort is not a sorting algorithm per se. Radix sort is a high level sorting algorithm that uses a basic sorting algorithm, right? So that sorting algorithm must be. Okay, so order n time is xi is polynomial, okay, but what if okay, suddenly I have just blasted, right? And no finite this thing, absolutely infinite set now. Okay.
But now you can sort it, right?
Yeah, so okay, now you can sort it. Yes. Sorting is reasonable, sure, and it will give you that whatever the sorting takes. So essentially what you're saying is that yes, I can certainly solve element uniqueness in the time that I require to sort. Right? Question is, can we do better? Right? So element uniqueness, let's call it EU, is reducible to sorting. That's what we are saying. So which means that the lower bound of element uniqueness should also apply to sorting, right? Okay. Okay, but then we are actually interested in the lower bound of element uniqueness, not about sorting. Okay. So, we cannot apply the sorting lower bound to element uniqueness, but we can do it the other way around. Okay. Now, all the lower bounds, not all the lower bounds, the famous lower bound or the most commonly known lower bound for sorting assumes a certain model of computation. And what is that? Comparison tree, right. So, what is a comparison tree model? Well, I mean, since it is not a decision problem, it is it's more than that. So, I am using the word comparison tree rather than a decision tree. So, you compare some elements x I x j, okay, and branch according to less than or some such thing, right. And depending on this thing, you keep doing it until you get your leaves, right. Leaves, each corresponding to a specific ordering. Okay. And therefore, number of leaves should be greater than or equal to n factorial, right. A leaf cannot have two possible orderings because
Greater than or equal to equal. Can there be more?
I mean, for my argument, I am going to use greater than or equal to. I mean, greater than or equal to also means equal to, right? Greater than or equal to. So number of leaves is greater than this, okay, and this implies that the longest path in the tree is at least log of this, right? So longest path which is about so this is your basic argument for the lower bound for sorting, and so the comparison and we do not actually count anything else, right. So the comparison tree model only counts comparisons, only counts comparisons. So this tree is only to count comparisons. If you are doing any some additions, some other things like assignments, whatever it is, other kinds of operations are not even being accounted for here. But it says that you are basically using comparisons to sort. You are stuck with this bound, right. And this is something that I have been alluding to a couple of times, that why should one only limit oneself to comparisons. Okay. So what is comparison? Comparison you can think about like I take two numbers x I, okay, minus x j, that is basically my comparison, right. So this is a special case of a inequality, a linear inequality where both coefficients are 1, right. So a more general inequality could be right. This could be another test, it's more general than comparison, but it's still linear, right. And why even have two x I x j, xi, xj, xl may be okay. I can bring in more dimensions. So, now it is looking like not like just comparing two elements, but in some dimensions okay, we are evaluating this inequality, or in other words, are we above a hyperplane or below a hyperplane? That is basically the kind of decision. Okay. So, the moment I do this kind of, I say that this is the operation that I am allowed to do in one step. Okay. The argument that we used previously is not going to fall apart, because if you have done the argument rigorously, it was only about these comparisons. Okay. So, somehow we need to redress that and see if actually that lower bound holds in this kind of a model. Okay. Right now, we are not talking about sorting, we are talking about element uniqueness. Okay. So, the model for element uniqueness is what I called a linear decision tree. So, decision, because we are discussing a decision problem, namely the element uniqueness is yes or no. Linear, because I am allowed to use only linear inequalities. Right. So, at any node, okay, I evaluate some linear inequality, okay, and again depending on less than or greater than or equal to a branch. Okay. In the end, in the leaf nodes, the answer is either a yes or a no, right? Maybe yes, 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 okay, no, 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 etc. How many leaf nodes should there be? This is not sorting. How many leaf nodes should there be? Not clear, right? Okay. So, certain number of leaf nodes, hopefully some kind of. So, any algorithm that uses linear decision, any algorithm that is using linear inequalities to decide on the next step can be captured by this model, which I am calling the linear decision tree model. Okay. So, there is this problem which is element uniqueness, and there is this then there is this model which is a linear decision tree model, and we have to somehow link up this problem and this tree. Somehow the structure of this tree, like in the case of sorting, we linked up the problem of sorting with some kind of structural properties of the tree, right, that had at least n factorial leaves. Okay. Here we can't even argue about that, because it is some kind of a decision problem. Okay. We can't say there are n factorial permutations or something. So, we need to be able to draw some linkages between the problem and this tree. That is how lower bounds are going to work out. Let me also just make a small remark here. I am discussing currently linear decision tree, okay, but similar arguments, of course, with more, you need some more tools to be able to handle that. You can you can model what is called an algebraic decision tree, where the basic inequality may not be linear, but it may be higher degree, maybe degree 2, degree 3, whatever. Okay. So, those are called fixed degree, I am just mentioning it, fixed degree algebraic decision tree. Okay. So, that is one variation. Other variation is even more general. Okay. Why even fix the degree? I can actually, when I do computation, okay, I can raise a number to any power that I want. Why should we be constrained? And I can raise it to any power by repeated squaring, which means that in very small amount of time I can really sort of blow up the degree, right. I can go from x to x square to x square square, x square square. So, in I steps I can compute x to the power 2 to the power I. Okay. So, why should we limit ourselves to only fixed degree? I can actually compute x to the power n very quickly in polynomial time or whatever, right. So, then you talk about what is called, the most general is called arithmetic computation tree. Okay. So, I am not going to discuss these variations, but it is somewhat closely linked to the discussion that we will have. Okay. So, today let me just talk about the problem space. Okay. So, the problem space that we have, the input is this tuple, this n tuple x 1 to x n. So, now for a moment just think about the input as a single point in n dimensions. We have an n tuple. Okay. I am thinking I can consider this n tuple, okay, as a point, as one point in n dimension space. Right. So, what do we gain by that? Not much, but actually it makes, although it looks complicated, it makes thinking somewhat cleaner. So, in that high dimensional n dimensional space, okay, certain points are yes points, right, which are where all elements are unique, all coordinates are unique. Some of these points, okay, they are not all unique, and therefore, they are the no answers. Right. So, in my space of, what is the space I am talking about? I am actually taking you to r to the power n, right. So, in r to the power n, okay, some subset, say W, okay, contains all the yes answers, okay, and the complement are the no answers. So, whatever my algorithm is, and if I am modeling it as a decision tree, in the end any point that I input, any point that is in R's of n, eventually should end up in a leaf node. If it is a yes instance, it should end up in a leaf node that says yes. If it is a no instance where not elements, all elements are unique, it should end up in a leaf node corresponding to this to the no, this thing, or the label of the leaf node. Okay. Just to give you a very simple example, in just 2 dimensions, okay, how does this space look? What is the space, or what is the set of points corresponding to yes, and what is the set of points corresponding to no? Yeah, right. So, that is it, right. This is my no, and this is basically W, right. So, in the plane, if you are talking about a plane, you can visualize this. As you go to higher dimensions, okay, you have to basically look at the intersection of these half planes. Okay. So, there are some half planes, or you call them half hyperplanes, so you have to look at the hyperplanes x I equal to x j, right, I not equal to j. So, in n dimensions, these are the hyperplanes, these are the hyperplanes that will contain those points that will correspond to the no answer, right, I not equal to j. And you have to look at what is called essentially the arrangement of these hyperplanes in this n dimensional space. Okay. So, union of all the points that lie on the hyperplane correspond to the no answer, and the complement of this corresponds to the yes answer. Any point that is not on any of these hyperplane, this is an n dimensional point. So, if that n dimensional point does not lie in the union of these hyperplanes, it means that all coordinates are unique. Okay. So, let us stop today, okay, and we will continue with that next time.